Hi, my name is Zain Al-Ahtab and I am a senior product engineer within Altair. And I would like to welcome you to this session in which we will talk about the electromagnetic simulation tools that we have in our portfolio within Altair. So our agenda for today is to start with a quick introduction to Altair's electromagnetic simulation tools, which are Feko, Windprop, and RAP, and to finish with a demonstration in which we will perform a quick antenna design and placement analysis, and then go through a virtual test drive performance analysis. So to start with a quick overview of Altair's electromagnetic simulation solutions, as I mentioned, we have our three main tools. So Feko, in which we are able to perform antenna design and optimization, and we will also be able to perform antenna placement analysis. So to try to see how the placement of the antenna will affect its pattern and its performance. We have also Altair Windprop, which is our tool for wave propagation and radio network planning. And the third tool is RAP, mainly used for spectrum management and co-site interference analysis, but not only. We will see that RAP has also other application domains in which it is actively used. So to start with the key features of Feko, as I've mentioned, we have the antenna design applications, so where we are mainly interested in optimizing a specific antenna. So firstly, creating it and then analyzing its performance and optimizing it to perform the requested outputs, let's say, given the application and the communication system on which we are working. We can also perform some antenna placement analysis, as I mentioned, so adding certain platforms on which this antenna can be mounted, whether it's cars, aircrafts, ships, or any other type of platform. We can also perform some electromagnetic compatibility analysis, as well as scattering and RCS analysis and other applications, some of them in the biomedical domain, etc. So when it comes to Windprop, Windprop is actually a reference software which focuses on wireless analysis, mainly related to radio coverage and radio channel modeling, but also deployment and optimization of radio networks, as we can see here. And we are able to perform some virtual flight tests for antennas and perform some analysis related to the performance of these antennas when they are placed in a bigger environment, in a more real environment. And we can also perform some coexistence and radio networks and electromagnetic exposure analysis within Windprop. Coming to RAP, so the key applications for RAP are related to wireless coverage analysis, some radio coverage, as well as satellite communication and satellite footprint simulations and analysis as well. We can also perform some co-location and co-site interference analysis in cases where we have multiple antennas, part of different communication systems coexisting in a very small area or environment. In this case, we see an aircraft which has 3 different antennas, and where we are interested in seeing the interference between these 3 different communication systems, and in case there might be some negative interference effects on the performance of the different systems. And we can also perform spectrum management, which is one of also the key features of RAP. So to give you an idea of how the tools can work together, for example, we will try to show that by showing you how the workflow goes for a virtual test drive. So for example, let's imagine we have a blade antenna. So you can model that in Feko and calculate the radiation pattern of that antenna accordingly once you have designed it. But then you can also move on to computing the radiation pattern once it is put on a platform. For example, in this case, we have an antenna, a blade antenna, which was placed on a helicopter, for example. And then you are able to see the radiation pattern which results from this positioning or this placement. So after we see this, we obtain these simulation results, and we can clearly see the effect of the placement on the antenna pattern. We are able to perform some virtual flight tests, for example, here within Windprop. And actually, the main goal is to also analyze the effect of the environment, and more specifically the multipath effects on the performance of the communication system. So the power, the received power, etc. So this is a way, one of the examples where we are able to complete our electromagnetic analysis using these multiple tools. So the interface of Feko, actually, once you launch Feko, you will have access to what we call the Feko launcher, from which you can run different tools, whether Feko, Windprop, or RAP. We also have a fourth tool, which is called New Pheasant, and it's mainly to complement Feko for specific cases of electromagnetic simulations. You can also have access using this launcher to all the documentation that you might need, starting from user guides and going all the way to example guides and other documents that will be helpful for you to as references, whether if you're starting new with the tools or whether if you're an advanced user and you need some extra information. So moving forward into a bit of more details related to Feko and the graphical user interface and specific workflows. So Feko actually has two main interfaces. The first interface is CAD Feko, and as its name might show, it is the CAD interface where you are able to create your geometry or import geometry files you have access to from other specific CAD tools. You are able to assign different material properties to your geometry. You will also be able to set your sources, your frequency solution, and all your requests. So whether you're interested in outputs such as far fields or near fields, currents, etc. So all this you are able to do in CAD Feko. You will also be able to set your solver settings, so choose which numerical method will be used during the solver runs. And our second interface is actually post Feko, where you will be able to visualize all the results of the entities you had requested in CAD Feko, and you will also be able to perform different types of post-processing. So in this case, we are viewing a far field of an antenna which was placed on a car, and we can perform different types of plots, 3D plots, 2D plots, and as I mentioned, some different types of post-processing also is available. Now, one of the main strengths of Feko is actually its capability to have multiple solutions for the users within one package. So actually, depending on the complexity of the materials you have and the electrical size of your problem, you will be able to define your solution method based on your numerical capacity. So based on the numerical resources you have on your machine. So we have two types of methods which are available, what we call the full wave methods, which are actually physically rigorous solutions that solve directly Maxwell's equations. And these methods are the method of moment, the MLFMM, which is an accelerated version, let's say, of the method of moments. We have the finite difference time domain method, the finite element method, but we also have asymptotic methods for high frequency approximations based on high frequency approximations. And so these Asymptotic methods become more interesting when we have electrically large objects or geometries in our model. And these methods are the UTD and the PORLGO, which stands for physical optics and ray launching geometrical optics. So we have a broad range of electromagnetic solvers in one package, and we also have the possibility to hybridize certain methods between full wave methods and asymptotic methods, depending on the geometry and the details of the geometry. So let's move forward a bit into antenna design and analysis. So here, I will give you a general idea of different types of antennas you can model, but not limited to this list. So you can perform some wire antenna design, and you can use these methods as solver methods, so the method of moments and the MLFMM, as well as some planar antennas, some antenna array design, and we have a specific array tool which we have recently added to Feko, and I will talk about it in a bit. And we have different solutions methods that you can use for this type of antenna models. But also, if you have more complex and more detailed antennas, or even bigger, electrically bigger antennas, you also have the possibility to model them and to start using some asymptotic solvers depending on the element size in your geometries, etc. And the bigger we go in the electric size, the more interesting becomes the use of the asymptotic methods, such as the physical optics and the ray launching optics. So this is to give you an idea about the broad range of antenna types that we are able to model and the different numerical methods that can be used for that goal. So in these cases, we have some patterns which result from specific antenna design. This is a case of a wire antenna. Here we have the pattern of a blade antenna, and we have also some simulations for an antenna array. And as you can see, these simulations have been performed over different frequencies. So to give you an idea of the range of the frequencies that we are able to run, and we will see in detail an example where we will be able to show the strengths of the tool when it comes to simulating over wide ranges of frequencies. So coming back to the antenna array tool, which was recently introduced in CAD Feko, you are able now to create your antenna array based on a unit model, which you will create initially, and you will be able to duplicate this unit to create the full antenna. But what you will be able to do is that you're not only duplicating the geometry, but also you are able to duplicate the ports and sources. So this will help you gain a lot of time while designing your antenna array. Now, on the other hand, Feko has a big component library. This library has about 50 plus models of antennas, which are available for you to include in your project. So instead of starting from scratch, you have a big range of antennas that you can choose from. You can visualize their patterns before creating and adding in your model, and you can also specify the frequency at which you want your antenna to perform, and the model will be integrated in your CAD Feko session. You will be able to perform different modifications to it if needed, etc. But this library does not only include antennas, but it also includes some platforms. So for example, here you have the model of an aircraft, a helicopter. You also have a model of a car, a mesh of a car. So all these models are available for you to use. and are already included in the antenna library. And this library grows with each release, so there are always new antenna models or new platforms included in this library. Moving on to some antenna placement and installed analysis performance. So we have here multiple examples. So some examples for antenna performance after the antenna is placed on a car, for example, for multiple frequencies. The case also of an antenna placed on an aircraft, again, at 2 different frequencies. And the third example is an example of an antenna array, which is placed on a ship. And we can see here also that the rough sea surface was also accounted for in the simulations, and also simulations performed at different frequencies. So another type of problems is that when you have multiple antennas that you need to place on one platform, and in this case, each antenna performs in a different communication system and at a different frequency. So one issue is that you need to perform some analysis for placing these antennas and to analyze the mutual interference effect between these different antennas. So in order to do that, you can perform different runs and different simulations for each antenna separately, and then analyze the interference effect. So in this first case, we have a VHF antenna. It's a cone antenna placed on an aircraft, and we are at a frequency in the range of 120 megahertz. We have also the amount of unknowns that the solver needs to solve. So when you see triangles, the triangles are the triangles of the mesh of our geometry, and they correspond to the number of unknowns that we need to solve. So for this case, it took Feko 2 minutes to solve it on an 8-core machine, and it needed 2 gigabytes of memory to be able to perform this computation. Now, moving a bit up in the electrical size, the same platform was used, so the same aircraft, but in this case to analyze the placement and performance of an S-band antenna. So in this case, we are at a frequency of 2 gigahertz, and thus the electrical size of the aircraft is much bigger than before, than the first case. And in this case, we are solving around 7.8 million unknowns. And in this table, you can see a bit how Feko performs for this type of problems in time, but also in memory requirements and per combination of cores. And these are all performed on this machine. So you can see that it scales quite nicely with the number of cores increasing. The required memory remains relatively acceptable, and the runtime, of course, decreases accordingly. Now, to summarize a bit what I have mentioned so far, so this is a table that allows you to see a bit the power of the EM solvers within Feko. So the power in the sense of the ability for us to perform different simulations at different frequency ranges, starting from 2 megahertz going all the way up to 3 gigahertz. And the numbers you see here are all numbers related to solving and simulating the case of the ship with an installed antenna on top, and by using multiple frequencies for the antenna. And here we can see all the methods that were used for the different runs. So we start with the method of moments, we move up to the MLFMM with the frequencies going higher and higher, and then we start using the hybrid methods. So hybridizing the method of moments with the physical optics and with UTD, and we see how that scales. So actually, this is quite a big strength of Feko and its solvers for our users. Moving on to Windprop. So Windprop, actually, as I've mentioned, it's a radio wave propagation and network analysis tool. So moving from Feko, after having designed and analyzed and obtained the patterns of the radiation patterns of our antennas, we can include them in Windprop. where we will also define the surrounding of our antenna. So the environment, whether it is an urban environment with buildings or an indoor scenario where we are interested in analyzing the propagation inside a building or inside, like, for example, a campus. So staying in small areas, but also moving all the way to rural propagation cases where the terrain effect comes into interest to be able to perform proper analysis. So to go a bit more into details related to regarding the workflow. So we first start with the antenna placement, as I've mentioned, and that is done with Feko. So the design, in some cases, we have to do reverse engineering instead of designing from scratch, and we can perform some analysis about the placement and integration of this antenna, all this in Feko. Once we move into Windprop, we have the possibility to perform some RF coverage simulations and access some received power results and channel response, line of sight analysis, and much more. We also have the possibility to add a specific air interface. So if we're interested in Wi-Fi communication or in LTE or 5G, etc., you can define that in your simulation project within Windprop, and you will be able to perform some post-processing for network planning, from which you will have access to all these outputs, including data rates, throughput, cell assignment in your area. So that is the network planning part within Windprop. Now, going a bit back to the type of scenarios we are able to model in Windprop. So we have three main types of scenarios. So what we call the indoor scenario, which can be the inside of a building, but not limited to that. So it also can be in the vicinity of the building or multiple buildings that form a campus or an airport. And the idea is that within indoor scenarios, we are analyzing the geometries in 3D. So taking into account all the geometrical details of the different objects present in our environment. We also have the urban scenarios, in which we are mainly interested in analyzing the effect of the propagation in a neighborhood or in a city. And in these cases, we need the database of the city with all the buildings, etc. And we also have rural scenarios where the main goal is to analyze the propagation over wider areas. And here the effect of the irregular terrain might have a direct effect on the propagation of the waves, and thus on the received signals in different areas of this rural area. But we also have the possibility, as I've mentioned, to add systems, so to define air interfaces. So if you're interested in some cellular systems like LTE and 5G, some WLAN, WiMAX, Wi-Fi, etc., all this is available for network planning within Windprop. And Windprop has multiple tools, but this is one of them. One of the tools I chose to share with you today, and it is a tool that allows you to perform some time variant analysis. And what we mean by time variant analysis is that one or more of the obstacles or the objects you have in your propagation environment is not static like a building, but is a moving object like a car, a pedestrian, a bicycle, etc. So what we are able to do is that we can perform car-to-car communication, but we can also perform car-to-infrastructure when the car is analyzing its environment. And what we see here are all the multipath interactions and rays, which are part of which are adding or affecting the received signal, the power of the received signal. So this is to give you also an idea about the different tools that we have within Windprop. Coming to RAP, So RAP is a tool which allows us to perform even bigger analysis. And what I mean by bigger analysis is that we are moving to bigger areas and a wider scale. So we are within RAP, we have the possibility to perform large-scale radio and radar coverage analysis, for example. We can do some spectrum management and monitoring. We can also do co-location interference, as I mentioned before in one of the slides, where you have an aircraft with multiple antennas for different communication systems, and you need to analyze the interference between these different systems. And we are also able to perform some satellite footprint analysis, like in different cases, with a footprint on Earth, so the coverage of the satellite, but also perform some satellite communication between different satellites. So again, the simulation within RAP is actually at the level of provinces and countries. We can add clutter map information, and usually we do not add any building information like we do in Windprop. We have a wide range of methods, so multiple ITU models are available in RAP for you to use for your prediction or your analysis in order to perform radio and radio coverage or some spectrum management related applications. So now I would like to move to a demonstration in which we will check together, get to know more the graphical user interface of Feko, and to do some antenna design, quickly analyze its placement on a platform, which is going to be a car, and then move to a virtual test drive. So when you launch your Feko launcher, you will be able to choose between the different tools. And for this demo, I will start with Feko, which we will use first to build our model and to analyze different parts of the performance of the antenna. So first, let's start by creating a new project. And what I will do first is I will use our component library to choose one type of antenna on which we will perform some analysis. So this is mainly our Feko interface. You have here on top a list of ribbons. And all these tabs that you have here, actually, if you follow them, they will guide you through the workflow within Feko. So first you start by constructing your geometry, you define your source, you define your requests, you mesh your problem, and you run your solver. So let's start by choosing a component from our component library. So here you can scan through different types of antennas and geometries. And in this case, let's start with the simple blade antenna. Once I click on blade, I will be able to view here the model, a preview of the model, but you can also have a preview of the antenna pattern, as well as some other patterns, some 3D patterns and 2D patterns. And you also have some tips on which solvers to use when you want to run the Feko simulator. So let's choose the normal blade antenna. And let's choose a frequency of 500 megahertz. And I will keep the solver type for now set to the default. We will keep the ground plane, and we will click on Add to Model. So it will ask us first if we would like to change the position of the antenna, but in this case, we're good. We're going to just keep the default settings. And we see that the model has automatically been added to our project. So what we see here is our blade antenna and surrounded by a ground plane. Now, note that you have access to all the geometry parts under this construction tab, under geometry, blade, You will be able to modify, if you want, the design after you have imported it, do some changes in the geometry, etc. So all the models you have in the component library are fully parametric models. So after, it's as if you created them from scratch. They are not geometries which are protected and you have to use as is. So that is an important point to know. So let's see. So our antenna has already a predefined port here, and we will try to launch the simulation. But first, we will also define specific requests. So let's first check our configuration. Under the configuration tab, we can see what type of sources have been defined for our antenna. So in this case, it's voltage source. And let's run our simulation. And to run the simulation, we will, before that, let's check, I missed a step. Let's check our far field request. So in order to add a request, so to tell the Feko what would you like in output, you can choose far fields, near fields, you can do some error estimation analysis, you can request some currents, and so on. And in this case, we'll perform a basic far field request where we will ask for, yes, a far field request, but let me perform a full 3D request here. So let me apply, and you see all the far field points that we have requested over phi from 0 to 360 degrees and theta from 0 to 100. And we will run our solver. So first, let's save this as Blade. And here we will see the progress of our solution. You can also expand the details. And we see that it has finished. So once we click on OK, now that the solution has been computed, we want to visualize it. And as I mentioned, in order to visualize it, we need to do that in PostFeco. We can launch PostFeco under the Solve tab, or we can also have access to it here in this small button. So let's see our results in our far field and how our antenna performs. So under PostFeco, first thing we are able to see is, again, our geometry. And we have access to our results under the Results tab over here. We would like to create, to add the far field we have just computed. So I will right-click on far field here and add to active view. Let's zoom out a bit. So this is our far field. Let me change it into dB. So this is actually our pattern. And here you have some options where you can remove the grid, make it only the surface to make it smoother. So if you have multiple requests here you have asked for, near fields, you can also plot them. We can also plot the far field in a 2D view. So here we are viewing our far field at phi is equals to 0 and over theta from 0 to 180. You can add multiple plots, etc. So let's go back to CAD-FECO. And let's try to analyze, to add this antenna, to place it on a platform. So let's create now the project in which we will perform the analysis of that blade antenna. First of all, let's include our car model from the component library. So it's the platform on which we will place our antenna. Let's choose to add our model. So as you can see here, we have the full car model, but without the tires, of course. And we have access to all the construction details, all the variables, etc. So I will first set the frequency to 500 megahertz. Confirm that. And let's move on to importing our blade antenna. So again, from the component library, I will choose the blade antenna. I will confirm my choice. I don't want to add a ground plane in this case because the car is the platform. And again, this is set to 500 megahertz, and I will add it to the model. Now, first, I will need to place it correctly. By default, it is included at the origin of my coordinate system, but I would like to place it on top of the car. So let's snap to a place almost in the middle. Confirm. As you can see, now the antenna has been placed. Now it is a big, it's a bit big for normal antennas on the car, but it's because I chose a frequency of 500 megahertz. You can choose higher frequencies and then your antenna will be smaller. I chose this frequency for the runs to be relatively quick for this demo. So now what I need to do is I need to perform a quick rotation. So I will choose the blade. I will rotate it 90 degrees. I will first choose the origin of the rotation, which is the point of contact between the blade and the car mesh. And I will rotate it 90 degrees. And here we are. We have the preview of the our antenna. Now, I'm just checking quickly some meshing related settings. So I'm just going to make sure that the So let me zoom out to the whole model. Now that we have everything set, let's check our configurations. So we will perform a first run and we will request our far field over 360 degrees and 180 in theta. And we can also perform a range analysis, so between 325 megahertz and 675 megahertz, and I will run this. I will run the Feko solver by using the MLFMM method. So by choosing it from the solver setting tabs, and here is where you have access to all the different solvers and their settings, and we can launch the Feko solver. We can check the details and the progress. You have also access to any errors, warnings, notifications. So here I have one warning related to a mesh element, but it can be, of course, enhanced, but for this demo, it won't have a big effect. We're almost at 45%. And waiting for the final phase. So here in the window, you have access to the progress of the simulations and all the details. And the run is done. So let's launch PostFeco to view our results. We have created. So of course, again, we see our geometry. And when we go to the under model browser, the results tab, I will choose the far field and add it to the current 3D view. Let's remove the grid, keeping just the surface view, and we can toggle to dB view of ours. So this is basically the far field of the blade antenna due to its position on the car. We have also here multiple possibilities, parameters we can use. We can plot. Here we are viewing the total gain. We can view the theta component, the phi component, and other elements. We can perform some post-processing in some cases. Let me go back to total. I can also plot some 2D views again of some far field cuts, etc. So what I would also like to do is I will try to compare and view it with the pattern of the blade antenna without the car. In order to do that, I will add the model within post-Feko of the blade I have created. So here it appears in the model list, and I will try to, again, add the 3D pattern of the blade. And we can clearly see that the presence of the car has affected, of course, the pattern. Now, after we have obtained the pattern of this blade antenna on the car, so the far field results, I will show you quickly how we can use them in Windprop and in urban scenarios. So here I have already prepared an example of a receiver. So basically, it's a car with the antenna pattern of we have just created using Feko, and this car will be actually moving in an urban environment. In this case, it's a neighborhood in Frankfurt, and we will analyze the received signal by this antenna located on the car from a base station. So here we see in blue our base station and the whole trajectory of the car. Now, what we have access to here is actually, first of all, in order to create your project, you need your what we call the database. So all the database, including the buildings or the objects present in the environment of propagation. And we also need, so as I mentioned, the antenna patterns, and we can define different air interfaces, etc. So I would like to show you, for example, the results we obtain by performing a propagation analysis over this trajectory of the car going through the streets in this specific path. And so the colors you see are the different received power levels by the receiver. And we can also view, so that was the 3D view, and here I've toggled to the 2D view, and I will also show you the different multipath rays we can visualize within Windprop. So here in the 3D view, we can see for each specific position of our receiver, all the interactions due to the multipath effect of the environment, which have an effect on the received power. We can also perform an animation, which is interesting to view because it allows you to see you can save it, but for the time being, I won't. So here you can see all the rays moving all along the trajectory and the effect of different buildings appearing and disappearing, the rays from which are appearing, disappearing, based on the position of our receiver and the position of the car on its track. So I hope that this demo was helpful, and this introduction in general about the electromagnetic simulation tools we have in Altair gave you a better understanding, and we will be shortly starting a Q&A session. So if you have any questions you would like us to answer, please do not hesitate. And thank you very much for your attendance.